Welcome to this joint session of Section 7, Lie Theory and Generalization. I am Michael Pevsner, professor of Reims University in France. It's my pleasure to introduce Joel Kamnitzer, professor of the University of Toronto. Joel Kamnitzer got his PhD in 2005 from the University of California, Berkeley, under the supervision of Alan Knudsen. Professor Kamnitzer has made groundbreaking contributions to representation theory in its geometric, higher categorical, and combinatorial parts, as well as in relations with low-dimensional topology and mathematical physics. The title of his ICM talk is Perfect Basis in Representation Theory, Three Mountains and Their Springs, as the picture shows. So please.
Thank you very much for the introduction, and thanks for the opportunity to speak. So indeed, I'll try to explain a bit about what this image means. So we have three mountains, and each one has a spring coming out of it, and together they're casting this rather evil-looking shadow over here. Oh. Oops, sorry. Ah. Okay. Hopefully this behaves itself. Okay, there we go. Okay, so let's begin with the talk itself. No more mountains. So the talk will be based on the representation theory of semisimple groups. So let's let G be a semisimple group. For example, the group SLN of n by n matrices of determinant 1. These groups have a nice classification of their irreducible representations. Usually they're denoted V lambda, and the index set for the irreducible representation is called the set of dominant weights. For example, in the case of SLNC, the set of dominant weights is a set of weakly decreasing integers modulo simultaneous scaling of them. So it's a subset of the weight lattice, which is z to the n mod z. So what do we study about these irreducible representations? The first thing that we study is the weight space decomposition. So every simple group has a maximal torus, and we can decompose our representation under the action of the maximal torus into eigenspaces for the action of that maximal torus, and that gives us these weight spaces. The weight spaces are labeled by the set of weights, which are the set of one-dimensional representations of the maximal torus. The second thing that we might be interested in is tensor products of representations. If we have two such irreducible representations, we form their tensor product. It decomposes the category of finite dimensional representations of semisimple groups is semisimple. So we get a decomposition, direct sum of your other irreducible representations, and there's some multiplicities. So here's a natural question, which as representation theorists have studied for some time, is to determine combinatorial formulas for these weight and tensor product multiplicities. In other words, to determine the dimensions of these weight spaces and to determine these numbers, the number of copies that V nu inside of such a tensor product. So this is an old problem, and it was only really first solved in complete generality by Littleman and Berenstein-Zelevinsky. Roughly in the same time in the 90s. So one approach to solving the problem, which roughly speaking was followed by both these people, is to begin by finding bases for the representations. So a nice basis of the representation, and it should be compatible with these weights and tensor product multiplicities. So what does that mean? Well, for weight multiplicities, it's kind of clear. You want a basis which restricts to a basis of each weight space. For tensor product multiplicities, it's a little less clear, but here's the idea of how it should work. So there's a way to embed a tensor product multiplicity space. So this here is a vector space whose dimension is c lambda nu nu. So this is a vector space recording the number of copies of v nu inside the tensor product v lambda tensor v mu. And this lemma, which is kind of classic lemma, shows us that we can embed this tensor product multiplicity space back into a weight space of the representation. we take the map phi, the map from v nu into the tensor product, we apply it to the highest weight vector, v nu. We evaluate on the dual of the highest weight vector in the second tensor factor, and we land at something in the first tensor factor with the specified weight. So not only do we have such a map, it's injective, and we can explicitly describe its image. So its image is the set of all vectors in this weight space, which are killed by inappropriate powers of these elements EI, and I should have written here, EI in the algebra of our group is the Chevalley generators. In the case of SLN, EI is an elementary matrix, a matrix with just 1 in one entry and zeros in all other entries, and that 1 occurs just above the diagonal in the I plus first slot of the matrix. And here I is the index set for these EIs, or you could say the index set for the set of simple roots. So this tensor product multiplicity space is embedded inside our representation, and it's explicitly described as vectors which are killed by a big enough power of EI. The power depends on mu. Here rho is the usual half sum of the positive co-roots. So this motivates the following definition, which I guess is due to Gelfand and Gelfand and Zolovinsky. A basis for a representation is called good if it's a weight basis, that means compatible with the weight space decomposition, and compatible with the kernels of powers of EI for all I. So that means for each I and each possible exponent you might put here, you get a subspace of your representation, and it should, good basis means it restricts to a basis of each of those subspaces. So that's a lot of conditions, because that's a lot of different subspaces that you have to restrict to. So it's not obvious that you'll be able to find a basis which is compatible with all those subspaces. So this is a good definition, but now we want a perfect definition. And the idea is, well, if we're going to talk about some behavior with respect to kernels of powers of EI, maybe we should be a little bit more precise about how our basis behaves under the action of EI. So here's a definition. So a basis is called perfect if it's good, so it's like the above, and if we take one of these EIs and we take one of the basis vectors, either the basis EI on the basis vector will be 0, okay? Or, well, the simplest thing you could say is that EI on B would be some other basis vector, EI tilde of B. So the simplest thing I would write here is EIB equals EI tilde of B. But that's not quite true. First of all, there's a little coefficient in front, epsilon I of B. Epsilon I of B is the nilpotence degree of B with respect to EI. So how many powers of EI are needed to kill B? And there can be some error terms, which are vectors with smaller nilpotence degree with respect to EI. So by looking at some simple examples like adjoint representation of SL3, it's easy to see that you do need to allow yourself to take some of this error term here. So this is the notion of perfect basis. And what's so good about perfect bases? Well, the main thing that's really nice about it is that it carries a combinatorial structure called a crystal. So what do I mean by that? So you have your basis of a representation, and now you're going to forget most of the information. You're going to forget the representation. You're going to forget exactly, what each basis vector is precisely in that representation. You're just going to remember 3 pieces of information. One is the weight of each basis vector. So each basis vector lives in a particular weight space of the representation. So it has a weight. So you're going to remember the weight of each basis vector. You're going to remember this EI tilde business. So like, what's the leading order behavior of applying EI to B? So it's some other basis vector, EI tilde. And I write ... because it's not defined always. Sometimes EIB is 0. So there's a partially defined map, EI tilde. And the other thing you remember is this epsilon I, which is this nilpotence degree, which is derived from, like, it's the same as the number of times you can apply EI tilde. So you have 3 pieces of combinatorial data, which are linked, because this changes, the EI tilde will change the weight in a predictable way. So remembering the basis as a set, along with these combinatorial data, is called the crystal. And here's a remarkable theorem of Berenstein and Kazhdan, which shows us why this notion is a really good notion. If we have 2 perfect bases for the same representation, so we might imagine, and we'll see later, that there actually are more than one possible choice of such a perfect basis. If we have 2 different perfect bases, well, those basis vectors might be slightly different vectors in our representation, but this crystal completely captures the information. So the B and the B prime are isomorphic as crystals. And even the converse is true. If you have 2 different representations and perfect bases in each of them, then they're isomorphic as crystals if and only if the representations are actually isomorphic. So the crystal really captures the same information as the representation. So I hope I've convinced you that these perfect bases are really nice. Maybe I should have said from the very beginning, or or quite soon, that going back to the fundamental question that I posed here, if once you have such a perfect basis, or even a good basis, you can answer this question simply by counting the number of basis vectors with certain properties. So if you count the number of basis vectors with that are killed by big enough powers of EI, you'll be counting the dimension of this vector space, so you'll be counting the dimension of this vector space, so you'll be getting your tensor product multiplicity. So that motivates these 2 questions. The first question is, how can we construct perfect bases? So in order to be able to use this theorem of Berenstein and Kazhdan, there's no existence result here. It's a uniqueness result. So we need to actually be able to construct the perfect basis. And how can we study the combinatorics of perfect bases? So in order to answer those questions about tensor product and weight multiplicities, we need to be able to count the number of perfect basis vectors, or the number of crystal elements satisfying some properties. So we need to get our hands on that combinatorics. Right. So there's many combinatorial models that have been developed for crystals over the years. And today, though, I'm going to focus on what's called Mirkovic-Vilonen polytopes, well, since that's what I like. And these were developed originally by Jared Anderson and then by myself, but they're also closely related to previous combinatorics studied by Lustig and by Berenstein-Zelevinsky. So I've been talking a lot about this crystals and polytopes. Let's see an example. So let's take the adjoint representation of SL3. So that's SL3 acting on its Lie algebra, which is the trace 0, 3 by 3 matrices. And here's the weight diagram of the representation. So the 2 here comes from the 2-dimensional space of diagonal matrices. Diagonal matrices of trace 0, that will be 2-dimensional. Okay? So and then when we do our crystal, or when we do our perfect basis, each one of these numbers will be replaced by an appropriate number of basis vectors. So 1 basis vector always on the outside, and 2 basis vectors in that 0 weight space. Those basis vectors will then be represented in this combinatorial model by polytopes. And here are the polytopes. And finally, I didn't draw it, but maybe I'll just draw it right now. There's going to be a crystal structure on these polytopes, so crystal operators will go like so. So this red guy will be E1. And there'll be another crystal operator, let's say blue, which will be E2. Okay, so that's the crystal of this representation as given by MV polytopes. So these MV polytopes are 2-dimensional. It has to do with the fact that the rank of SL3 is 2-dimensional. If we go to SL4, our polytopes become 4-dimensional. Sorry, 3-dimensional. Here's an example of a SL4 MV polytope. Here's another example of a SL4 MV polytope. So they're a lot of fun. And these MV polytopes, I won't describe it, but there's some explicit description of them. So they're exactly polytopes satisfying a certain condition on all their two faces. So it's very easy to build them or make a computer make them or whatever you like to study them that way. Okay, so that's the combinatorics. Let's go back to the first question. How do we get our hands on perfect bases? So there are three known constructions of perfect bases, and this is the three mountains at the beginning. So the first construction, this is like roughly in historical order. The first two constructions are due to Lustig. The first construction is called Lustig's canonical basis. And it has many different possible sources. In some sense, it really is kind of canonical, in that it can be made in many different ways. For example, Lustig's original construction using quantum groups, other constructions using categorification. So this basis has many different sort of mountains that it comes from. In this picture, by the way, which is due to, the idea of that picture is due to Arun Ram. The actual picture you saw was drawn by my daughter Bella, but the idea of the picture is due to Arun Ram. And his concept was that these bases are like the rivers, and they come down from those mountains, and the MV polytopes are the shadows of the mountains. Okay, so Lustig's canonical basis, we discussed that one. Next is Lustig's semi-canonical basis, and it comes from the geometry of quiver varieties. Finally, there's the Mirkovic-Vilonen basis, which comes from the geometry of affine Grassmannians. These two bases are dual in a certain sense via the theory of symplectic duality, which I'll not talk about today. But one thing I do want to just mention is that under that duality, these two bases are kind of switched, and this basis is invariant. It's another way in which the canonical basis is sort of more canonical than the other ones, more perfect. Okay, so I'm going to discuss, somehow I'm going to discuss 3 and then 2 and not really discuss 1. Okay, let's talk about the MV basis. So to begin with discussing the MV basis, I need to discuss a space called the affine Grassmannian. So I begin with the Langland's dual group of G. So it's just another semisimple group. For example, if we started with SLN, the Langland's dual group would be PGLN. I form its affine Grassmannian, which means I take this G check over the field of the Laurent series, and I quotient by the subgroup, which is G check over the field of power series. So for example, I take like invertible matrices where the entries are the Laurent series, that's a group, and I quotient by the subgroup, invertible matrices where the entries are power series. This is a kind of flag manifold, like a kind of G mod P, but for this an affine Kac-Moody group. So an infinite dimensional version of a flag manifold. P, from the beginning of the talk, was the weight lattice of the group G, which means that by Langland's duality, it's the co-weight lattice of the group G check. So P is the homomorphisms from C star into T check. In that way, every element in P gives us an element in the affine Grassmannian, since it gives a map from C star to T check, and then you can regard that map as a Laurent series, give you an element T to the mu in the affine Grassmannian. So the affine Grassmannian, well, looks like this. This is a weird picture of the affine Grassmannian. This like yellow soup, and had little points floating in it. These points are these these points T mu. In fact, the affine Grassmannian has an action. Maybe worth writing that down. The affine Grassmannian has an action of this group T check, and the fixed points for this action are precisely these T mu's. Okay. So the MV basis comes from the geometric Satake correspondence, which I'm not going to get into because it's definitely a topic of a different lecture. But what I would like to say now is that the MV basis is indexed by certain subvarieties of this affine Grassmannian. So to each of these special subvarieties of the affine Grassmannian is associated a basis vector. So how do we get from these subvarieties? Oh, and I didn't really say, these subvarieties are called MV cycles. So they came before the MV basis, or before the MV polytopes. So if we have such an MV cycle, we can form the following construction called the moment polytope. In this case, we can define it using a moment map, but here it's much simpler. We can just say, we just simply take the convex hull of all mu's, these weights, or co-weights of G check, where t to the mu lies in z. So here's a z, for example, it looks like, and it contains 3 of these things. They could lie in the interior, but I just didn't draw any big enough ones, so they were not in the interior. So here I have 3 points, 3 of these mu's, where t to the mu is in z, and I join them up and I make a triangle. So that's my picture of z, or my polytope of z. Here's another polytope of z, of a different z. So for example, those 2 triangles, if you remember back in the example of the adjoint representation of SL3, the 0 weight space, which was 2-dimensional, was represented by 2 triangles that looked a little like these 2 triangles. Those 2 triangles are the moment polytopes, or the polytopes of 2 different copies of P2, 2 different MV cycles which are isomorphic to P2. In this case, those guys are toric, and for those people who know toric geometry, these are the polytope corresponding to P2 as a toric variety. In general, it's a bit misleading because they won't usually be toric. But in any case, there will be some polytopes associated to each of these MV cycles. And then I proved that the map that associates to each MV cycle its polytope gives a bijection between these MV cycles, which I didn't quite mention what they were, and a certain explicit set of polytopes, which are called MV polytopes. So those polytopes that I've been talking about, which can be described combinatorially by the set of polytopes satisfying certain conditions on their 2 faces. So this is actually a bijection between this MV cycles and the MV polytopes. And therefore, the MV polytopes will index this MV basis. Okay, so that's the MV basis and how it's related to the polytopes. So let's go to the second topic called semi-canonical basis. So now we assume that G is what's called a simply laced, so that means of AD type. There's some stuff you can do if it's not, but just for simplicity, let's go in that direction. We're going to consider the Dynkin diagram of G. So for example, this would be G is SL5, so his Dynkin diagram is A4, 4 vertices in a line. And we're going to choose, so I is still going to be the index set of this Dynkin diagram, and Q, the vertices of the Dynkin diagram, Q will be a choice of orientation of the Dynkin diagram. So to each edge in the Dynkin diagram, I'm going to choose some direction, and I'm going to call Q that set of arrows. Then I'm going to sort of immediately forget about that choice, and I'm going to double my quiver. So I'm going to put arrows backwards in the opposite direction, and I'm going to call those guys, the collection with its doubled arrows, Q bar. Okay. And maybe one last piece of notation, which I didn't write down, but the original arrows are going to be called, say, A, then the new arrow will be called A star. So now I form the pre-projective algebra of my quiver. It's defined as follows. I form the path algebra of this doubled quiver. That means it's as a vector space, it consists of the free linear combination of all paths in this doubled quiver. So you go like this, and go here, whatever. And you mod out by the ideal generated by this relation, which is that A star minus A star A. So going one direction and going back. What this has the effect, it's not completely obvious, but it has the following effect. That a lambda module, a module for this algebra, is a graded vector space, graded by the by the vertex of the Dynkin diagram. So one vector space at each vertex of this Dynkin diagram, along with maps going back and forth whenever you have an edge in the Dynkin diagram. And there's a condition, and this condition, the pre-projective relation, ends up meaning that if you go start at some vertex mi, and go to all the outgoing ones, all the things that are connected to it, and then come back along the backwards arrow, So you follow the composition like so, and add it to the composition like so, and add it to the composition like so. The sum of all those will add up to 0 with appropriate signs. So the sum of all the ways of going out and back from a given vertex will add up to 0. Usually, sometimes there's only one way of going out and back, and usually there's only 2 ways of going out and back, but sometimes there are three ways of going out and back. Okay. So what are we going to do with these lambda modules? So given a lambda module, it has a notion of dimension vector. So rather, since it's a graded vector space, we can record this graded dimension. We take the sum of the dimensions of each of the mi's and kind of use alpha I, the simple root alpha I, as a placeholder to sort of separate them, and we get a dimension vector, which is sum of dimension mi alpha I. Now we're going to fix some sum of vi alpha I. Vi's are natural numbers. And we consider lambda v the variety of all lambda module structures on a fixed vector spaces of dimension vi. So this is an affine variety. It's a subvariety of a product of spaces of matrices. So this product, it sits inside the product of all the spaces of matrices from vertices to from some, what you see here, from CVI to CVJ. So over all edges in this doubled quiver. And it's a subvariety because cut out by this pre-projective relation, that the sum of all the ways of going out and back is 0. Maybe. Well, before the theorem, let me just do an example. So imagine we're just in the case of SL3. So our Dynkin diagram is of type A2, so we just have 2 vertices. Then we have 2 arrows, the original one and the reversed one, so I'll call those guys A and B. So a representation of our quiver would consist of, a representation of our pre-projective algebra, which consists of 2 vector spaces and 2 linear maps A and B, and the sum of all the ways of going out and back is 0. Well, there's only one way of going out and back, so you get AB and BA both have to be 0. So for example, if we take, so this would be for arbitrary mi's, but we could restrict to the case where we could restrict where so here we have m1, here we have m2. Then if we took m1 equals c equals m2, in other words, we take this v1 to b1 and v2 to b1, then these matrices A and B just become single numbers A and B. So here we just have 2 numbers whose product is 0. Well, one order, the other order the same. So we just get this coordinate cross as the affine variety. And as you see, it has 2 irreducible components. Okay. Oops. I realized I missed the definition. Okay, one second. So, okay. So, okay, so here we have, back up slightly. Okay, so here we have 2 irreducible components. In general, we have some variety, this variety of all lambda modular structures. It's called sometimes Lustig's nilpotent variety, and it has many irreducible components, and we're interested in studying the irreducible components. So the way we do it is by means of this polytope, but I actually realized I forgot to write down the polytope, so let me do that right here. So we define the polytope of a module to be what we might call the Harder-Narasimhan polytope. So it's the convex hull of the set of all dimension vectors of submodules. So I take the convex hull of dimension vectors of submodules. So that's like an example. So for example, suppose I take any point in this y-axis, maybe non-zero point in the y-axis, so some generic point in the y-axis. So it consists of a copy of C, a map in one direction which is non-zero, and a map in the other direction which is 0, because somehow the lower number b is the x-axis for some reason, and the upper number a is the y-axis. So, a module like so will have a submodule sitting at this vertex. This copy of C here, this vertex is a submodule because when you follow this arrow, you get 0. So it is a submodule. So the possible dimension vectors of submodules are 0, alpha 2, and alpha 1 plus alpha 2. Then we arrange them into a polytope. On the other hand, if we take this module, then the non-zero arrow will go this way. So this copy of C at this vertex will be a submodule. It has dimension vector alpha 1. And we get a possible dimension vector 0, alpha 1, and alpha 1 plus alpha 2. And we get this, take their common home, we get this triangle. And these are the exact same two triangles I've been showing you all along that represent the two-dimensional zero weight space in the adjoint representation of SL3. And so this is the general phenomenon that we proved with Pierre Baumann, Peter Tingley. So if you want to study these irreducible components of Lustig's nilpotent variety, you can do it using these MV polytopes. And how do you do it? You just take a generic point in your irreducible component and form this Harder-Narasimhan polytope. And that will give you a bijection between these irreducible components and the same MV polytopes we had from before. So what's really remarkable is that we had two totally different looking geometries, one about affine Grassmannians, and there the polytopes came as these moment polytopes, recording which torus fixed points were inside our MV cycles. And here we have totally different geometry of the quiver varieties, and our same polytopes come, this time recording something about dimension vectors of these modules, or dimension vectors of submodules of these modules. Okay, and actually if we went to the third mountain, the one producing the Lustig's canonical basis, we'd actually get the same polytopes again, and that was a theorem of Tingley and Webster, and they proved that the same polytopes arise as what's called character polytopes for modules for KLR algebras. But I don't have time to go to that one, so I'm going to go in a slightly different direction. Okay, so far we've seen, well, this complicated geometry, these mountains, giving us basis vectors, so MV basis, semi-canonical basis, and then both of them sort of giving the same combinatorics, MV polytopes or crystals. So this is great from some point of view, a very pretty picture, but it's not great from one perspective. So when we take SL2, SL3, and SL4, and maybe also SL5, it's not known yet, there is a unique perfect basis for each representation. So those representations, I mentioned these perfect bases, not only do we have in existence, but actually every perfect base is exactly the same. Not only do they produce the same combinatorics, there's actually only one possible choice of basis vectors. But that's actually not going to be true in general for other groups, in particular for SL6. But this combinatorics is not enough to tell apart the basis vectors, because the combinatorics is almost sort of designed so it only knows about the crystal. So the MV polytopes won't be able to tell apart the basis vectors. So we need to introduce some kind of finer invariance for our bases. So this finer invariance takes two forms, sort of. The first form, that may be most natural, is to introduce a measure supported on the MV polytope. For the MV cycles, this measure is called Dorsmet-Heckman measure. I won't talk about those measures today because it's like, so I have a slightly simpler approach, which is if you take this measure and you apply Fourier transform, and you take a certain coefficient of that Fourier transform, you'll get a rational function. So there's a way of turning this measure into a rational function, and it's these rational functions that I'll talk about today. Okay, so what are these rational functions? So associates, I mentioned we have these MV cycles. I mentioned that they have an action of a torus. Well, I mentioned that affine Grassmannian had action of a torus, and the MV cycles are invariant for the action of the torus. And all these MV cycles that I'm talking about today, they all contain a special point, the point t to the 0 in the affine Grassmannian, called the base point of the affine Grassmannian. And anytime you have a variety with an action of a torus and a fixed point for the torus, you can talk about the equivariant multiplicity of the variety at that point. This is a notion introduced by Briand. This, one way to say this is it's a class in the localized equivariant cohomology of that fixed point, and therefore it lives in the space of rational functions on the algebra. And it measures the equivariant topology of the variety, the MV cycle, near that fixed point. For example, if that fixed point is a smooth point of the variety, then this would only depend on the tangent space, and it would be precisely 1 over the product of all the weights of the torus acting on that tangent space. So another way to say it, it measures how much this thing fails to be smooth. But it's easily computed using methods of commutative algebra once you have equations for your variety. Okay, now we're going to match that with something on the lambda module side. Okay, if I have a lambda module, then we can consider composition series. So composition series means you take a flag of submodules of your module where each quotient is simple. So, for lambda modules, like for quiver representations, being simple is a very restrictive condition. It means the module is very simple. It's just one-dimensional and concentrated at a single vertex. So the simple modules are just labeled by the vertices in the Lincoln diagram, and they're all one-dimensional. So we would say that this quotient, subquotient, mk over mk plus 1, would have to be a specific simple SIK. So where ik is some vertex in the Lincoln diagram. So given some sequence of vertices in the Lincoln diagram, I can consider the variety of all composition series of type I. So it's a kind of flags of submodules of M of a certain type. And it's a projective variety, and we can consider its topological Euler characteristic. This was studied by Geist, Leclerc, and Shor. These topological Euler characteristics of these varieties of composition series. And now we're going to kind of arrange these numbers into a sort of weird generating function. How are we going to do it? First, for any such sequence as before, I introduce a strange rational function, which is 1 over alpha I1 plus alpha I2, and so on up to alpha I1 plus alpha M. That's a little hard to read there. So it says, I should say alpha I1 dot 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 alpha IM. Then I form this invariant of M called d bar by summing over all possible sequences like that. I take the Euler characteristic of that variety of composition series, and I multiply that by my rational function. And, well, I get a rational function. Okay? So these things are not linearly independent. So this is not it's less information than remembering each one of these things. So it turns out by the work of Geist, Leclerc, Shor, remembering each one of these Euler characteristics is equivalent to remembering the semi-canonical basis vector. So I want to forget a bit of information, but not too much information. So that's why I'm multiplying by these things. It turns out to be the right information to forget. And there should be a bar on this. The reason why there's a bar on this is because there's another di without a bar. Anyway, he's not going to appear on the talk. So here's the theorem we proved with Pierre Baumann and Alan Knudsen. So we start with an MV cycle and a lambda module. I call it generic lambda module because it's like a general point of some irreducible component of Lustig's nilpotent variety. So I start with MV cycle and a generic lambda module. And associated to the MV cycle, there's an MV basis vector. This is the construction that I didn't explain, but uses the geometric Satake correspondence. There's also a semi-canonical basis vector. This, again, I didn't really explain, but it's due to Lustig and studied by Geist, Leclerc, Shor. And I'm interested, so I have those two of my two perfect basis vectors, and I'm interested in checking if those two vectors are the same. And maybe I already checked that combinatorially they're the same. They produce that same MV polytope that I've been talking about. So here's our theorem. If the two basis vectors are the same, then their refined invariants will be the same. This equivariant multiplicity, this topological invariant of the MV cycle, and this generating function thing related to composition series of M, d bar of M. So both of them are possible to compute with enough work. And so we did that with, the same people, and Andronowski and Calder, Morton, Ferguson. And we found that in the case of SL6, we found an explicit example of a certain MV cycle. It's like a 16-dimensional or something MV cycle, and a specific example of one of these lambda modules where the two refined invariants are not equal, and therefore the basis vectors are not equal. And so that was the application of the theory. Okay, and well, I'm a little early, but I'll stop there. Thank you.
Well, thank you very much, Professor Kamnitzer, for your talk. Thank you very much, Professor Kamnitzer, for your talk. If you wish to interact with the speaker, you may join him on Discord, following the link available on the VICM website. Thank you.